All right, so now we're going to take this control volume analysis and apply specifically the conservation of mass to it to see how we do that. So you are familiar with the control volume concept from thermodynamics. We have a specified volume, in this case, of course, of fluid that contains fluid, and we're going to use conservation of mass on that. Now, you know from thermodynamics that conservation of mass can be written this way. The amount of mass change in the system as a function of time is going to be equal to the mass flow that goes in minus the mass flow that goes out. Now, for an arbitrary control volume like this, a kidney-shaped control volume, something with an arbitrary shape, we want to use something that allows it to have that. So we're not going to just call it mass. We're going to relate this to the kinds of properties that we study in fluids, the kinds of properties that fluids have and that can be measured. So we're going to change dm dt to be the more general term. I mean, it's exactly the same, but that applies to a volume. So that would be this. So now we're saying that dm dt can be written as the change in time, change with respect to time, of the density integrated throughout that volume. So that's going to be your mass term. Notice that this volume could conceivably increase or decrease. So if the volume is not a fixed size, that also could change the mass. If the volume were suddenly to shrink, this form takes into account the fact that, yeah, okay, if you're going to shrink that volume, we're going to have less mass. So that makes sense. And then so we can rewrite, all of that in terms of the conservation of mass equation that we already are familiar with. Just putting that on the left-hand side. You got m in and m dot out here. But we want to convert, those right-hand terms similarly to something that is more amenable to fluid mechanics. So m dot in minus m dot out can be rewritten as this. Now, you may not have seen this since Calc 3, but hopefully it'll come back to you. So here we have an integral representation of m dot in minus m dot out for a fluid. So we've got the density, no surprise there, of course, if mass is flowing in and out, density is what's going to make that happen. But we also have the velocity vector. So anywhere on this volume, there could be a velocity, and that velocity could be bringing mass into the system, or it could be taking mass out of the system. That velocity, of course, changes as we go around the surface. That velocity, but the only velocity that matters is the velocity actually on the surface. In terms of whether mass is entering or leaving the system, it doesn't make any difference if there's velocity in here. That makes no difference at all. But if velocity crosses, brings matter across the boundary, then that matters. This term, this u dot n, that's a dot product. N is defined as the outward-facing normal. So n is the outward-facing normal from our volume. So it has a magnitude of 1. It's not going to change the size of u. But what it's going to do is tell us whether u is pointing in, or u is pointing out, or u is pointing to the side. If u is pointing exactly perpendicular to n, that is right along the surface, then it's not carrying mass in or out. No mass is changing. And so that's what, the dot product actually goes to 0 when the two vectors are perpendicular. If the vectors are aligned, so u and n are the same way, of course, that's bringing the maximum amount of mass out of the system. And so that's what this negative sign is saying. If u dot n is aligned, that's going to decrease the mass in our system. Right? It's going to decrease it. If u and n are opposite in direction, so let's say, for instance, here's n here, maybe there's a mass, a u here, well, that's going to bring mass into the system. Again, the negative sign will give us that. So we're going to have the u dot n product will then be negative. The negative sign will make it positive because mass is going to flow into the system. So this term represents that. It represents the in and out. So we can now write the mass conservation equation in terms of integrals, which is what we like to do in fluid mechanics, because our systems are always fluid. That is, they can change size and shape. And so we want a very flexible way to represent that. So we have this equation that the conservation of mass is that. So here's the change in mass integrated over the whole volume, and this is the change in, this is the inlet and outlet. So this is mass in and mass out where you integrate over the surface to determine that by taking that velocity vector, u vector, and dotting it with the normal, outward-facing unit normal. All right, so that's an important equation. That's your conservation of mass. Now, in many cases, as you know, we have discussed, we have incompressible flow. And as we've also discussed, incompressible flow is actually much, much more common than incompressible fluids. Incompressible fluids include many things, basically all the liquids we study. But incompressible flows often include gases, because even gases are often can be treated as incompressible if they're not going too fast and if they're not heating up or being cooled down or compressed. So for many cases, we can treat things as incompressible flow. But at any rate, when it is incompressible, we can say, obviously, what that means is that the density is approximately constant. And so we can pull the density out of these terms. So we have density times the change in dV here, right? So there's no density there. And then we have, over the surface area, also the density can be pulled out. And u dot n hat is integrated over the surface. And then the densities simply cancel. So that's interesting. So then we say, all right, well, this is just the volume. This is just a volume integrated dV. So that's literally just V. So that's dV dt, because that's just the definition of the volume, essentially. This thing here, that's just volume. And then this thing is what remains to be. It's kind of an interesting term. So this is the u dot n hat still integrated over that surface. But now we see that the volume change, if there's more mass flow in than there is out, then the volume has to get bigger now because the fluid is incompressible. So more mass means more volume. And similarly, if mass starts to leave, the volume has to decrease. So this takes that into account. But in many cases, we also have fixed volume. So if we have fixed volume, which we often have in many of the engineering applications we'll be using this for, we end up with a very simple equation, which is that the integral of u dot n hat integrated over the surface has to equal 0. So if you have incompressible flow and you have fixed volume, then this is conservation of mass. Incompressible flow and fixed volume, the integral over the surface of the velocity vector dotted with the outward unit normal, integrated over the surface, has to be equal to 0.